All right, let us begin. Very exciting times, in my opinion, because we now have this really fancy tool in our toolbox, right? It's called Laplace. And you've had lots and lots of fancy tools already. Algebra, right? That's a fancy tool that not a lot of people have in their toolboxes. And you evolved into calculus, which is another really fancy tool in your calculator, but you don't pull that one out all that much because it's a tool that you got to spend a lot of time tweaking and adjusting to be able to get it to work, right? So it's not the easiest tool to use, but it can do some pretty powerful things. Laplace is another really, really fancy tool. And as long as we are fairly comfortable using algebra to do our partial fraction expansion, it's actually a pretty easy tool to use. And we can do almost all the calculus stuff that we need to do, especially for real world systems, by using Laplace. So set up our tables, make sure we understand our tables. And then now we're going to convert. Our next step is to convert all our physical systems that live in the real world. And we're going to focus this class on electrical systems, but other disciplines, mechanical, chemical, they all have other systems that they will convert into the Laplace domain as well. So we're going to figure out what we need to do to convert our standard devices, and then we'll start doing circuit analysis and then see if we can get pretty easy results. So let's start out with the easiest. It's just the resistor. So a resistor in the time domain is just Ohm's law, right? And you'll notice this is where we change a little bit because in previous circuit analysis classes, you said V equals I times R. Well, we're going to add a little bit to that because this is time varying. So it's V of T equals R times I of T, right? Because the voltage can change over time and the current can change over time. So those are time varying values. My resistor, though, is fixed. We're not going to be changing the resistor because if the resistor was allowed to change, we could get some real problems. So how do we convert that to the Laplace domain? So the Laplace domain transformation for V of t is going to be equal to the Laplace domain transformation of R times I of t. And do you remember the mathematical property of multiplication by a constant in the time domain? What is that equivalent to in the Laplace domain? When we multiply a function in the time domain by a constant, what is that equivalent to in the Laplace domain?
Does it stay in multiple? That you can multiply it through?
Yeah. If it's a constant, it's the exact same thing. You multiply a function in the time domain by a constant is exactly the same as multiplying that Laplace domain transformed function by that exact same constant. So you can see here, R just gets moved out front. All you have to do. And now in the Laplace domain, we have V of S equals R times I of S. So a resistor in the time domain looks like a resistor in the Laplace domain. So if we're trying to draw an equivalent circuit element, we know that on the left there, your time domain representation is your resistor. Same exact resistor in the Laplace domain. They are identical to each other. No modifications necessary. Exactly the same. All right, any questions on that? Kind of just like AC circuit analysis, right? So if I write a resistor in AC, or we'll call it steady state, it's the same resistor, isn't it? There's no J omega or 1 over J omega C, right? It's just R. It's all it is. So I don't have to do any modifications, just like we do in the time domain. All right, now let's look at the inductor. And if you recall, V, the voltage drop across an inductor, is equal to L times the rate of change of the current going into the inductor. So this isn't exactly Ohm's law, is it? Ohm's law says V equals IR. This is nowhere near Ohm's law, but it has kind of a close look. It just includes the derivative. So now let's go and do the same thing we did for the resistor. We're going to convert everything to the Laplace domain and see how we end up. So the Laplace domain transformation of our voltage is equal to the Laplace domain transformation of L times di dt, or I prime of t, we'll just substitute there. Isn't this L right here a constant just like the resistor? It's not changing. So move it out front. If we can multiply by a constant, it's exactly the same as we had as the resistor. What changes a little bit is now that we have the Laplace domain transformation of not I of t, but I prime, or di dt. And when we take the derivative of a time domain function, what is that equivalent to in the Laplace domain? Kind of on the board for you. Taking a derivative is the same thing as multiplying the Laplace domain transformation of that function, in this case I of t, times our variable s. So we have to multiply by our variable s. And if you recall, when we did the derivation, we also have to subtract the initial condition. So this I0 here is the same thing as saying I0 in the time domain. Notice the lowercase I. Okay, so that is our circuit. So remember how in the resistor, it looks exactly the same. In the case of the inductor, the voltage is equal to, in the Laplace domain, is equal to S times L I of S minus L times I0, the initial condition. So if we want to draw that as a circuit equivalent, here is what our modification becomes. Okay. Notice I have an inductor and a voltage source, or I have an inductor and a current source. And either one of these is equivalent, right? Because they're just a Thevenin and Norton equivalent, so you can go back and forth. So this is how you need to modify your DC circuit in the time domain, or doesn't have to be DC circuit, your circuit in the time domain, and convert it to the Laplace domain. We've got to add a power source, and we have to add the value S to make it work. Any questions on that? Important that we see how we got those. All it is was just the math. Okay. Physics gave us the equation L di dt. We actually do the math to end up with an equivalent circuit that doesn't have any derivatives, right? In the Laplace domain, V of S equals S times L I of S minus L times I0. There's no derivative there. It's just multiplication by S. So we're going to do the same thing and modify our circuit. So in the Laplace domain, we have this circuit. All right. Questions on that? Because these two are very important, because this is what your circuit model is going to look like. Instead of an RLC, you're going to have an R and an L with potentially a power supply and the S multiply there. And the capacitor one, we're going to see it in a second. Questions on that? Feel okay so far? All right, let's do current capacitance. So physics gives us the equation I equals C dV dt. Let's do the exact same thing we've done in the previous two cases for the resistor and the inductor. And we see that we take it to the Laplace domain. We have L in our current is equal to the Laplace domain of C V prime, or dV dt. Multiply by a constant, we can move the constant out front, we have C. Now we have to take the Laplace domain of V prime of t, which is multiplying by S and subtracting the initial condition. And we end up with SCV of S minus CV naught. Schematically, if we want to represent those schematically, like if we actually want to draw what the equivalent circuit diagram is going to look like, Same exact thing. We have a capacitor. That's no longer just a capacitor now, right? We have 1 over SC. And we either have a power supply that's a voltage or a current, just depending on your application. And you'll notice it's got either the CV naught or the V naught divided by S. It really just depends on which one you're trying to do. And that comes from here. Okay. Just a Thevenin or a Thevenin equivalent to go to the series equivalent or go back to the parallel equivalent. Now, one thing that I'm trying to be not really sneaky about, but trying to sort of emphasize, what do you notice about the power supply for the capacitor? What is it based on? What is it? V naught, very good. Or the initial voltage, right? What about the inductor? I naught. Any guesses as to why I used V naught and I naught up here? There's a reason.
Is it because that's
A
part
darn.
of, is that
All right.
because, is that because it's part of the differential equations for current and voltage across a inductor or capacitor due to time?
Well, yes, but you'll notice I flip-flopped, right? One's the current, one's the voltage. Why did I use current for the inductor and voltage for the capacitor?
Well, you have to, because there would be a discontinuity if you swap them.
But I could have written the initial equation over here, right? Instead of saying L d I dt, I could have used the integral, right? I could have used the voltage initial condition. But why did I use I and V? Henry's got it. Can the current instantaneously change in an inductor? No. So if I use the initial condition of current, all I need to do is find the current. If I wanted to use voltage for my initial condition, then I would have to do another circuit analysis to figure out what that voltage is going to be just after the switch transitions. So by using current here and voltage here, I don't get any instantaneous changes. I don't have to go there. So when you're given a problem and somebody says your initial condition is blah-de-blah, that's what you can show in the circuit. If I was doing the opposite, then I would actually have to do another circuit analysis technique and go ahead and solve those initial conditions, which I do not want to do. So this is the easier way to analyze them. Much, much easier way to analyze. That's it. R, L, and C circuits. That's all we have to worry about in this class. Because those are pretty much all the devices you'll ever come across in industry. You might have some nonlinear devices. You might have, a couple of diodes and whatnot, but you wouldn't necessarily be looking at them in this way, in this capacity. So what do? When we come to a circuit, we get rid of the R, L's, and C's, and we replace them by the Laplace domain equivalent circuit. The resistor is the resistor. The inductor is either one of these, depending on what you're trying to analyze. And the capacitor is one of these. So you replace the circuit, including the initial condition, right? So that's where we got to tweak it a little bit. Then the next thing is now we are writing, and you should really highlight this, algebraic equations. For those of you who have taken ECE circuit analysis, I think it's 209 and 210 and 210, not 2010, but 210. That is a much different way to solve circuit analysis, right? Homa, did they do differential equations down at Southern Maine to solve it, or did you just assume everything steady state? Arthur, they did a 209, right? Where you did to look at transients and you had to do all that stuff.
I took 210 and 214, and yes, we did have transient responses.
Yes. And the way that you probably solve those in those classes is with Laplace, right?
Oh, absolutely.
Yeah. So we're going to actually do the same thing that our colleagues in ECE do. And we're just going to do things and solve them algebraically. No differential equations. If you want to do them differential equations, that's fine, but you're going to find out they're much easier to do algebraic, even when we do partial fraction expansion. So we've got algebraic equations, and we use the exact same circuit analysis techniques that we do for resistive networks. Once we're in the Laplace domain, capacitors, inductors just look like resistors. You treat them exactly the same as resistors. And if I look over here, you'll notice it's 1 over SC. What if we let S equal to J omega? This becomes 1 over J omega C, right? Doesn't that look awfully familiar? Isn't that negative JXC? Isn't that when you do AC circuit analysis? That's what you do, right? You do negative JX sub C whenever you're looking at a capacitor. How about an inductor? J omega? So that becomes J omega L. Isn't that JX sub L? So AC circuit analysis is a very specific application of Laplace when you have a sinusoidally varying input. Then you just substitute in J omega. But for us, we got to do more than just sinusoids. We have to be able to do any input, any time domain input. We're going to keep it as S. So just like AC circuit analysis, where you do impedance terms and you do Ohm's law, which is V equals I times Z, you're going to do the same thing in Laplace. Then you're going to go back and do partial fraction expansion by doing getting the inverse Laplace transform. And you can get not only the transient response, but you can also get impulse response as well. You can get whatever input you want to go ahead. So let's take a look at a case where we have a simple circuit. And we'll substitute some numbers in a little bit here. We've got a capacitor that has some initial voltage on it, V naught. Our switch closes and then starts to feed the resistor. So if you remember, to solve this up until this point, you remember our y of t equation? Y of t is equal to, what is the expression? Y of infinity plus y of 0 plus minus y of infinity, e to the minus t over tau. Remember that generic equation? What is y of infinity going to go to if we're trying to solve for the current through the resistor? So let's rewrite this as I of t is equal to I of infinity plus I of 0 plus minus I of infinity e to the minus t over tau, where tau is equal to RC, right? In an RC circuit, it's just RC. So what is I of infinity going to be equal to for this circuit?
No current. Eventually, it's just discharge.
Yeah, it's going to discharge. You're going to get 0 current, right? 0 amps. What does I of 0 plus equal?
Oh, that needs some number crunching.
Does it?
Oh,
Ohm's law, right? You got
Right.
a voltage source that has a value, initial value of V naught. You got a resistor R. Isn't it just V divided by R? And tau is equal to RC. So if we substitute that here, I of t is going to be equal to 0 plus V naught divided by R minus 0 e to the minus t over RC. Everybody okay with that? So our final equation, V naught over R e to the minus t over RC is the final result that we'd end up with, correct? That's what we should do if we use our approach that we develop for those first order systems. How about now we do it in Laplace? So we convert the capacitor to here, and then we just do circuit analysis. So can't we do KVL here? Easy peasy KVL. negative V naught over S plus I times 1 over SC plus I times R, guts to be equal to 0, right?
Mhm.
And everybody know where I got this, right? I wasn't fancy. I just literally grabbed that from here. I did my series equivalent, so I just copied exactly what the series equivalent was and put it here. So now I can see that V out over S is going to be equal to I times R plus 1 over SC. Everybody okay with that? I'm going to solve for I, but first, let me put this under a common denominator. So that's RSC plus 1 all over SC. And so now I'm going to solve for I. So I is going to be equal to V naught over S times SC over RSC plus 1. The S terms will cancel. And let me put it up over here. I is going to be equal to V naught times S over RCS plus 1. The problem is I can't go to the Laplace yet because this doesn't match the table. Remember, it's always S plus something. So I factor out RC. Why do I have S? It's C. Sorry about that. That's C times S plus my C's will cancel, and I am left with this expression over here. In the time, if I go back to the time domain, don't I end up with exactly that expression? Exactly the same thing, right? V over R or V naught over R is just a constant multiplier, so I can move that out. And 1 over S plus 1 over RC becomes e to the minus T over RC, right? That's exactly what we would calculate if we did that memorization equation. But you can say, hey, wait a minute, Paul. That's more work than just using the memorization equation, right? And it's true, it is more work. However, if I have a second order circuit, I can't use that memorization equation. It doesn't work. So that memorization equation is only working for a very specific case where I have a first order circuit. The Laplace stuff over here works for however many resistors, inductors, capacitors you possibly could have. So it's more generic and it works for everything. So here's my final answer. They match. And you can sanity check it, right? We know that we get that here. But what about the initial condition? What should V or I? Yeah, what should I equal to when T is equal to 0? V naught over R, right? That's what we said earlier. If I plug in 0 for T, what do I get? E to the minus 0 is equal to? Yeah, e to the minus 0 RC is just 1. So you end up with V out over R, which is what we said when we did it right here. How about e to the minus infinity over RC? What do we get? 0. Isn't that what we said right here? So we got the same equation, but we also, double check our work. Questions on that? Super duper easy check, but a pretty cool one to go ahead and see that we got the right result. I want to do a more challenging one. I want to go to bed. Not a lot of energy here.
Oh, come on, let's do it.
All right, you guys want to do this one?
Ooh,
How about I give you 5 minutes to do this one? I've already converted it to the Laplace domain. Notice there are no initial conditions. So I would love for you to write an equation for IL. I'll give you five minutes. I wonder if this is disconnected because I'm not getting any output here. It's off. Shut the door. They're clearly disappointed in the test. Need more time? Yes, no?
A little bit would be helpful, thank you.
All right, 2 more minutes. Is that a fancy ice mocha latte green? Uh, yum. My wife likes Thai lattes that they get at Starbucks. We're making them at home because it was cheaper than like $8 for a. I'm not she gets, but all it is Tazo concentrate and milk. Pretty easy to make it. Okay. What do y'all got?
I've got a really big ugly thing that probably is wrong.
Okay. Anybody get anything that's not a big ugly thing that's wrong? Maybe a big ugly thing that's right? Can we use our generic equation on this one, the y of t equation? That'd be the greatest thing, wouldn't it? Can we use it?
No,
Why not?
it's a second order equation.
Yeah. You have an SL and a 1 over SC or a capacitor and inductor. You can't combine those. So as a result, this is at least a second order circuit. So you can't use that first order circuit. But when I look over here, why can't you just do circuit analysis? This says 1 over SC. Can I just call it R1? That's R. Can I just call that R2? Isn't it just a bunch of resistors?
It is.
Over here is a DC current in the Laplace domain. So you will notice I took this DC value and I used my Laplace properties table, which says that an input, which this is an input, right? It's a DC input to the source for the system. Whenever you have a DC input, you divide by S, right? It's just a unit step essentially. So IDC or 24 milliamps over S. And then my capacitor with no initial conditions just becomes 1 over SC. My resistor is my resistor. And my inductor just becomes SL. So I can do whatever circuit analysis technique I want to solve for IL. Anybody have a preference what they want to use?
I used current division, but
You can use current divider. Yep. That works perfectly fine. You can do nodal analysis. You can do pretty much whatever you want. All those circuit analysis techniques work. I'll show you what I did. I did a nodal analysis, right? I used KCL, and I'm assuming all the currents are going in this direction for the ones that are not known. So the current into the node is going to be equal to the current out of the node. So current into the node is IDC over S. That equals the current out of the node, right? which is V times, it's V divided by 1 over SC, and then I just inverted it, plus V over R, plus V divided by SL. And then I did some fancy math to go ahead and get to here. Does anybody need to see me do the work, the algebra, to go from this equation here over to here? Or do they feel like you want to see that? Okay. So let's copy that. Whiteboard. Okay. So generally the easiest thing to do is to factor, right? Try to get all the equations, if you will, the functions, if you will, all together. So IDC over S is equal to V of S times SC plus 1 over R plus 1 over SL. Everybody okay with that? Now I want to common denominator it because I've got a bunch of different fractions. And if I want to solve for V of S, I'm going to have to invert and multiply, right? Both sides. So that is equal to V of S, and that becomes times, common denominator here is S times L times R. So over here I have nothing, so that becomes S squared times L times R times C. Plus, I'm missing the SL over here. And I'm missing the R over here. Okay? Everybody following that step? Because when I multiply SLR, I'm putting it under common denominator. That means I have to multiply this SC by S times L times R. So it just becomes S squared. So now I can invert and multiply and see that V of S is equal to IDC over S times SLR all over S squared LRC plus SL plus R. Cross out the S's, right? Because those will cancel. Now, what's usually very helpful for me to do is to have the highest order S term, in this case S squared, multiplied exclusively by 1. So I said IDC and then I wrote IDD. I'm going to put LRC out front, and that multiplies S squared. When I factor out R, L, and C from there, from S term, what am I left with? Right? And over here, I'm left with 1 over LC. Those will cancel out. And I've got IDC divided by C times 1 over S squared plus S over RC plus 1 over LC. That's the math that I got to for here. Everybody agree that those match? Okay, so now I have my voltage, and you certainly can go into the time domain, but if you remember the problem description, what did I ask for? Did I ask for V or did I ask for I?
Yeah, you
I
have
asked for I. So given the equation for voltage, how would you solve for I?
just have to manipulate, I to the other side by itself. That's all.
There's not an I to the other side. This is a DC. This is an input. I'm solving
Oh.
for IL. So what Homer said is use Ohm's law. Just divide this voltage by, whoops, not LC, SL. Isn't that what Ohm's law would say? V divided by R equals I. R, quote unquote, in this case, is just S times L. So I'm dividing that by S times L. Okay? And when I do that, I've got to factor out my S term here. And then I move my L term over here. Right? You all need to see what I did there, because basically I'm dividing the right-hand side by S times L to get IL of S. That's all I'm doing. Okay? So now I'm going to plug in some numbers. I was smart, wasn't I? I didn't put any numbers at first, because look at the numbers, what they get to be. A little onerous, right? Not real fun. But that's okay. We're pretty good at this stuff. We can use our calculators. So when I plug in those numbers, you can see I get some fairly big or awkward numbers, which seems intimidating until I say, you know what, I can just use quadratic equation. And I can actually solve for the roots of this to figure out if there's real and equal roots, real and unequal roots, or are they complex conjugates of each other. And when I do that, I end up with negative 32 plus or minus J24 times 10 to the third. All right. If you don't like that, you can always go to MATLAB here. And remember, we just type in roots of, here are the coefficients. The first coefficient is 1. The second coefficient is 6.4 times 10 to the minus 4. 6.4 e to the 4, I think it was. And then 1.6 e to the 9. Close that. Exactly the same thing, right? Negative 32 plus or minus J24K. Okay, so the results of my quadratic equation match exactly. So I have to do partial fraction expansion. What case do I need to do for my partial fraction expansion? Remember case 1 was I had real and unequal roots. Case 2 was I had repeating roots. That would be real and equal. Case 3 is I have complex roots. Case 1, case 2, case 3. You tell me. Case 3. So I've got my A over S and my B at an angle of theta. I solve for A over S doing my approach, and you can see that I get 24 milliamps. Interesting. That's one of the numbers that we saw from the DC source. That's a good sign. To do my B at an angle of theta, a little bit of work, but I end up with 960 at an angle of minus 143.1. Now I'm going to set it up to match the table. So I've got S minus my real part, that quantity squared, plus my imaginary part. And remember, the sine term requires me to have omega in the numerator, which means I have to divide by omega. So my final IL of S has got to be 24 milli over S plus 40 milli at an angle of minus 143.1 times 24K over S plus 32K squared plus 24K squared. Those are the two partial fraction expansions. Now I take it into the time domain, and here's my final answer. Let's do our sanity check and see if it's correct. How much current should be going through the inductor under the initial conditions when the switch just transitions and the current source is into the circuit? 0, because the initial condition said IL of 0 minus is equal to 0. So IL of 0 plus should be 0. That's what we get here. But that feels cheap, doesn't it? I checked my initial condition, so yeah, it worked out okay. Which is interesting, right? Because when you plug this in here, you think, no way, you're going to end up with 0 or minus 24 milli, but it works out that way. But it feels a little cheap. This is a time domain expression. So let's actually see if it matches what we would have for an actual waveform. This is multisim, right? You've been using this in lab. Is this the same exact circuit that we've been studying up to this point in class, or this problem? Looks the same, right? And hopefully what you've been doing in lab is you've been doing transient analysis. So you simulate analysis. I set my initial conditions to 0, just like I did, or just like the problem spells out, right? The voltage and the current are both equal to 0. So I'm going to force those initial conditions to 0. I'm going to stop at a wacky time that'll make sense. And I don't want my maximum time step to be too great. My output is going to be I primary, which if you look at my original circuit, that's where I put my probe there. So I'm monitoring the current through the inductor. Anybody have any agena with what I've got there? Make sense? Agena? I don't know. That's Italian word, maybe? Have any stress? I hope it's not derogatory. I just think it means like stress. Maybe I should check and see. Agena. If anybody's offended by that word, I don't even know how to spell it. Agena slang. Oh, that's not what I was looking for. See, this is a thing. I apologize. Agena for stress. Term. Angina. How about this? That's where I've heard it. All right, maybe it's no longer a word, but I've heard it where you're giving me agina means you're giving me stress. You're stressing me out. So
Maybe it's spelled different?
yeah, I don't know how to spell agina, I guess. A-U-G-I-N-I. I don't know. But agina, yeah, maybe let's try that. Maybe it's A-U-G. That's angina. So maybe it should be angina, but they just said it funny to sound like agina. I don't know. Maybe that's where it came from. So I'm glad it's not a derogatory term. Yeah. All right. So we're looking for current. We're going to run it. There's our plot. This is what we should get, right? But Paul, you said you were going to compare that to this. Whoops. To that's whiteboard. There's a PowerPoint. Going to compare that to that. How do I know if that's right? This is where I'm going to teach you, hopefully, an incredibly powerful tool. It's called Excel. Excel is wonderful for plotting things and coming up with nice charts. So I'm going to enter in here 1 over 32,000. What do you think 32,000 is? It's not the current.
The time constant.
It is the time constant, right? So we know when we did the partial fraction expansion, we ended up with a real part to be 32,000, correct? So that is our equivalent time constant for the second order circuit. That's the 32,000. So I'm going to call this, and here's a really useful feature. Did you see how I call that tau? I've reassigned the cell, which should be A1. I've called it tau. And the reason why I call it tau is I'm going to be using that term a lot. And if you put it in Excel and you try to copy cells down, Excel tries to help you, but sometimes they make it worse. By incrementing numbers, they might go A1 to B1 or A1 to A2, and it just kind of gets all jumbled up. So it generally is a lot better for you to go ahead and define variables that way. So I just called it tau, T-A-U. Now I'm going to come up with a bunch of X coordinates times, and I picked 1, and then I just picked tau divided by 50. I want 50 points in between each time constant. And then this equation over here, 0.024 plus 0.04 e to the minus a3 over tau, which is e to the minus t over tau, times a sine of 24,000 minus 143.1 times pi over 180. Goodness gracious, what is that exactly? Does that look anything like IL? 24 plus 40, e to the minus 32,000. 24 milli plus 40, e to the minus 3. And if you invert this, right? Get 32,000, right? So I got that so far. And then I do sine of 24,000 times t. 24,000 times t. Minus 143.1, minus 143.1. What's with this whole pi times 180, pi divided by 180?
Convert degrees radians.
Right. So remember, when I give you the solutions, when I give you the complex numbers, I always show the little bubble to show degrees. I got to make sure I convert that to radian mode first, or radians first, because omega times t is radians per second times seconds would be radians. So I'm going to convert my degrees to radians to be able to do the calculation. So I just did that calculation, and then all you do is you copy it down. So you see how it's incrementing A4 to A5 and on and on and on all the way through, but the tau doesn't change. And here is the plot.
So were you able to write that equation once and place it through
Yeah.
and it automatically will increment itself?
Yep. I'll show you a secret. So I even did this one. I said this is 0. Then I added tau plus 50. And then look what I did over here. I did the previous one plus A4. And then on and on and on. I just added it to the previous one. So once I got to this one, I just copied it down. Okay. Same thing over here. And the way you copy it down, see my cursor here? It's like the big, it looks like a cross almost. Watch when I go to the lower right-hand corner. See how it gets black or fills in? You copy the cells down that you want to replicate. You just drag and drop.
It automatically knows.
Well, let's do it, right? I'll delete all these. Okay. There's zeros now. There's nothing in here. I'm going to go ahead and I'm going to just drag these right to here. And it went from here, which is A3. Now it's A4, A5, on and on and on and on and on. That's like the nice thing about Excel. But had I called this A1 and put that as A1 over here, then it would be A3 divided by A1. Then over here, it would be A4 divided by A2.
Yeah.
Does anybody know how to lock it in so it doesn't change? Make it call it a variable, which is, I think, the easiest way to do it. The other thing too is let's call this 34. And let's say that this is equal to this plus 1, right? And let's copy some down. And you can see it increments. What if I said, you know what? I don't want that to increment beyond here. So I'm going to say it's Q4 plus 1, but I'm actually going to put a $sign here. And watch what happens. So here's my $sign. Doesn't update it. Okay. So putting the $sign locks it into position. I also can go this way too, right? So I can say here, I can drag these over here. And you can see QR, it updates that way. If I don't want it to, then all I need to do is put the $sign with the Q. And then try bringing that over. And then it locks in. So the $sign can lock in either the row or the column. Or, like I said, for me, just call that one tau. And even if you click over, watch just very quickly. Look at the letter that you see up in this column right here. Just look very quickly and you'll see what happens. See, it says A1. Because Excel knows that as A1. but I've reassigned it as tau. And so then it's substituted in tau, and it doesn't, it takes a second for Excel to do it, but you basically, anywhere you see tau here, it just says, make it A1, and it puts the dollar signs in for you. So really, really, really helpful feature, especially when you're doing a lot of engineering stuff and you got all these numbers and variables and all that stuff. You just fix it with calling it a variable. Okay. So we spent a lot of time talking about it, but does this equal that? Starts at 0, goes up to around, I don't know, what is that, 20 something milli at 100 micro. Starts at 0, goes up to around 20 something at slightly more than 100 micro. So what do you know? We checked our work.
So
Go ahead, Arthur.
how would you change the axis label to be in microseconds on your Excel?
In Excel?
Yeah. Because see right now, yeah, you got pretty big.
So I format the axes, and let's see if I can change the number here. Display units, I want it to be in, I don't know if I can actually do it that way. Maybe text options, let's see. Mark showed you how to change it so that it displays. How about number here? Let's see. Category. Let's try scientific. That better?
Well, no.
No, it looks kind of like it's close to micro.
Yeah, but I want it to be, nice. I want it to look like it, microseconds with a little symbol.
Well, you can't do micro because Excel will plot it as a number.
Ah,
Can I make that go up to e⁻⁵? I don't know.
okay.
You might be able to do it here, but I'm not sure. I've never done that.
All right, I was just curious because it'd be nice, even if it was, use US, after each one. But I don't know. I just think it would be.
Yeah. No, it'd be cool, but again, Excel can do a lot, but I don't know if it can do everything you want. Because again, this package is designed primarily for accountants way back in the day, right? You do a balance sheet essentially, and you do that. That's what Excel will tell you. So yeah, they're more than consistent just by looking at the initial condition. They match exactly. So I'm feeling pretty good because multisim is telling me, here's my result. And that's just a circuit analysis. That's like, doing a simulation software. But I can do it with hand calculations and end up with the exact same waveform. Now, any idea why in this class we do a lot of simulation in this class and we don't do a lot of actual physical circuits?
Because you don't want to blow something up.
No, not in this one.
It'd probably be hard to like measure that with equipment.
That's exactly right. You better be ready to rock if you're going to be doing something in the microsecond level. So that happens so quickly, data capture would be very difficult. Now, anybody have any problem with some negative currents here?
No, it just means it's going against the direction that you chose.
Well, it wouldn't actually be negative. That is the problem with precision. Like when I did this work here, I said minus 143.1. It's probably minus 143.12, da, 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 da. You have to add in all those digits. And so if we were going to be exact, we'd have to add in all those digits. We're not being exact, we're being close. That's why we get some slightly small negative numbers. Where when you look over here, you don't get any negative numbers, right? If I display the points, so I drag it out a little bit, you can see all these numbers are positive, right? No negative numbers, even at the nano level. And again, we could get there in Excel if we just kept adding to the level of precision when we did our calculations, but you know, I think if you did 143 or what did I say the number was? Yeah, 143.1, that's close enough. I would say that these are pretty exact on. Questions on how to do this? Because again, we're EET, right? We like to talk about a lot of applications. And how would you do this in the real world? So you could use a simulation software, or if you don't want to spend $5,000 on multisim, you could do your own circuit analysis and you could just plot this in Excel. A lot of folks use Excel in industry, even engineers, just to keep track of things. We use Excel all the time. And so we're doing that here in Excel. Questions? Because now we can take that circuit and tweak it. And if we wanted to, instead of the input being a DC input, we can make it
A sine wave.
sinusoidal function. Yeah. This just becomes Im cosine of omega t. Right? So instead of I DC over S, we end up with that term. Everything is exactly the same. Exactly the same. Except now we have that one and that one. If you recall from before, the first term was just A over S. The second term was a B at an angle of theta. This here is our forced response. That's because the power supply is forcing the output to follow it to a certain extent. It's 24 milliamps over time with the DC source. With a sinusoidal varying source, it's going to eventually look like a sine wave. And we also have a natural or transient response. That's the actual circuit elements themselves, pushing and pulling and fighting and all that stuff until they've given up the goose and they're no longer fighting. Then the transient decays away. How can you tell if it's a natural or a forced response? The natural response always has a decaying exponential associated with it. It dies. It's going to decay away. The forced response does not die away. Because if you think about the real world, right, there's no system that has no resistance associated with it. So unless you keep feeding the system energy, that system eventually is going to be de-energized completely. That's transient decay. Where if you power it up with a DC, a sinusoid, or something, then you would just go ahead and you would have, that value that would keep on. Okay? So that's what we're talking about for the decaying sine wave and the steady state sine wave that does not have a decaying exponential. Questions on this? Because this is a lot of material. We've started using that fancy new tool, right? That works really well. But we also are using a lot of stuff that just circuit analysis. So taking our circuits and converting them back and going from there. All right, I'm going to be magnanimous because there is this much energy in the room. Is that a fair statement? Yep. So should I let you loose? That means no, you all want to stay for another 12 minutes?
Don't make no never mind to me.
Yeah, so sometimes as a teacher, you have to be able to read the crowd a little bit. And if I just continue pounding new material, I think that applies the laws of diminishing returns. So I'm not going to pound new material. I'm just going to make sure. What's that?
It's all
You saw the circuit signs?
No, I saw that we're gonna do that with mesh then, so. It's gonna be here.
Oh, so Luke brings up a really good point. I first did nodal, right, for here. That worked fine in Laplace. Over here, I can do mesh. You can do either one. Any circuit analysis technique. And I think Arthur was the one who said, hey, let's just do KCL to solve for the current. That would have worked perfectly fine. Current divider, yeah, I said KCL. Current, you can do
Yeah.
current.
But now that I look at it, KCL makes more sense than the current divider.
Okay, but it would work no matter what. You can do any circuit analysis tool that you want, that you've learned, and it works. Max power transfer works. Do you remember way at the beginning when we said Thevenin and Norton equivalent? That stuff works as well. So all of these tools that you've been working for or working to learn are 100% applicable here. So that's why you have mesh. So if you're bored over the weekend, try doing mesh analysis and see what you get. Give it a whirl. Okay?
We have a
Yes, so you have a test on Friday, right? Week from tomorrow. So do you want your test review on Monday? Or do you want it on Thursday? I mean, Tuesday or Thursday?
Thursday.
All right, we got to do a poll here because there's some difference of opinions here.
Well, if we did do it on Tuesday, is there new material?
It was everything that we did up until Tuesday. It's not even going to cover this.
Right, but are we gonna start going over the material for the test? Yeah, not on the exam, but.
Yes, we can't waste time, right? All right, let's do our poll. We launch it once Zoom wakes up. All right, TV land, you go and do your poll. How about people in real land? Do you want to do who votes for Tuesday? Who votes for Thursday? All right, the Tuesday folks have it because it was 5 out of 7 that voted. So it's basically the proportions on TV land are the same. So we'll do our exam review on Tuesday. So come with any questions. It's just going to be the exam, just going to cover up to the Laplace, just the introduction. None of the Laplace circuit analysis. We'll do that in the next test. All right, folks, have a great day. And we'll talk to you later. Take care, everyone.
All right, thank you.
Thank you,
Thank
Paul.
you.
Thank you, Paul.